to objects. It's a distortion in space-time, which is created by massive objects. So the most extreme example of this, I don't know if anyone here has seen the movie Interstellar. And in this movie, we have a very powerful black hole, and it bends light in an extreme way. So it's creating a very strong distortion. And from the movie, you can see that it's bending starlight. And when you're next to the black hole, even the light from the black hole is being melted and distorted like this. Anyway, so that's basics about gravity. And now we talk about the gravitational waves. So when we have very heavy objects like black holes, and they are orbiting each other, at some point they get very, very close together and they collide. And when these black holes are orbiting around each other, they're creating very, very strong waves in this fabric of space-time that we discussed. So it's as they're orbiting, they get closer and closer together, and they make these powerful waves and ripples in space-time that propagate through the universe. And this was just theory until 2 years ago when we figured out how to detect it. So we see here that this is the black holes, and they're dragging space-time and creating these waves. So we decided to try to measure this. And so how does this affect the Earth? When these gravitational waves, they pass through the Earth, they bend and distort the Earth like a tennis ball. And we want to measure this activity. So we decided to construct a very, very precise instrument. And this instrument is called LIGO. So the LIGO Observatory is, there's one in Virginia, I think one in Oklahoma, and there's one somewhere, I think, in Australia. So we have 3 of them. And this instrument basically is 2 very long tubes, and on each end is a mirror, and the laser that shoots through this, and I'll explain how that works. And this tube is a complete vacuum. So in this vacuum, you have the laser light beams, and you've got one arm which is in one direction and the other arm in the other direction. So what we're thinking is that if the Earth is being stretched and pushed like this, then the arms would become longer and shorter. But the gravitational wave is so small that we have to detect motion of the 1/10,000th the width of one proton, of one atomic nucleus. So we're looking for something extremely precise, a change that is so small that it's the same as the distance between, if we were measuring the distance between 2 stars, and the precision level had to be the width of 1 human hair. So we've never built anything so precise before. And again, we have laser beams here, and in the end of the laser beams, we've got these mirrors, and these mirrors are extremely precise, and they're very heavy, and they're made of special materials, and they hang from strings. So these mirrors have to detect the change of the 1/10,000th the width of one atomic nucleus, proton. And they hang from these special gold strings, and it's a very difficult to construct machine. So inside the machine, we have laser beams like this. So what are we trying to discover here? We're trying to discover that the arms of these things are changing in length. They're stretching and squeezing depending when the gravitational wave passes through the Earth and actually changes the shape of the Earth. So the Earth bends vertically and horizontally, and when the Earth is moving in both directions like this, the arms of the machine are getting longer and shorter, and we're trying to detect this change. So how did we detect this change? We have wait, where is the video for this? 1 second. Oh yeah. So this is basically the device, and we have we're trying to detect this. The arm is getting longer and shorter. That's what we're trying to detect. And we use a phenomenon called interference to detect this. So we have these laser beams that are being shot through the mirror, and then they split into 2 halves. And then they hit the mirrors on the other end, and then they come back together. And normally when there's no gravitational wave, the arms are exactly the same length. And when the laser beam combines, you have something called destructive interference. So you see here that the waves are canceling each other out. So the light cancels each other out. And like when you have 2 waves of water that crash into each other, you're left with nothing. So when the arms are identical, the waves are exactly opposite of each other, and there's darkness. So on the end here, there's a detector, and the detector doesn't see any light. It sees complete darkness. But once the arms start to stretch, the waves are no longer perfectly in sync because they're different lengths and the waves don't line up anymore. And when they don't line up anymore, you actually get light emitting. So you see here when the arms start to stretch, you'll see that the light comes in and out of phase. And so you have light being detected at the detector. So you see pulses of light that are the result of the arms of the detector being physically stretched by the gravitational wave. So this light pattern on this disk here is the evidence that the Earth is being stretched in two different directions by the gravitational waves. And so the first wave we detected, we did not expect that we would detect black holes halfway across the universe colliding in a very violent event. This was very unexpected. So, and when we made a mathematical model of what would happen when two black holes collide, the model lined up exactly with the light pulses. So we have the, back to this video when the black holes are getting closer and closer together. So the gravitational waves are getting closer and closer. It's like and it comes into a pulse. So you see here along the bottom of the video, we have the frequency of the waves. And as the black holes get closer and closer together, you see that they're getting faster and faster and faster. And as they're about to collide, the waves get really fast, and then silence because they now merge and collapse into one object. So this exact pattern of waves, closer and closer, closer and closer, and then silence, that's exactly what we detected, the pulses of light in the detector. So when we see and we're sure of this because we have two different detectors in different parts of the world. So both detectors at the same time, halfway across the world, saw the same exact pattern of light pulsing. So it tells us it's not an accident because the detector is so sensitive that even if you have a truck or a car driving 100 kilometers away, the car bouncing on the road 100 kilometers away can upset the detector. It's that sensitive. So the pulses we detected are the same, the pattern, as the chirp, the noise of the black hole. So let me actually see if I can turn the sound on. It makes a noise. I don't know if anyone can hear that, but it makes a weird noise. And that sound you're hearing is the sound of two black holes 15 billion light years away colliding in a massive explosion. And that's insane. And this event of these black hole collisions is so powerful and so violent that it released more energy, 10 times more energy than the entire universe shining. So all the stars in all the galaxies in the entire universe still produce 10 times less energy than this collision of black holes. It's the most energetic event in the entire universe. Nothing can compare in terms of the amount of energy that's released. So this is a very, very interesting thing. And we're launching now detectors into space where instead of these arms being, tubes in the ground, we have different satellites, which when the, when the gravitational waves pass through, the distance between them changes. So it's much more sensitive. So what's the outcome and what's the result of this? First of all, we've proved that Einstein's theory of gravitation is 100% correct. Everything about it is accurate. And this was the last thing we'd never discovered. Second of all, we can use these waves as a new form of telescope to explore the universe, which is extremely interesting. And we can also prove various theories about the formation of the universe because we still see ripples from the birth of the universe in the Big Bang. So that's the main point. And another interesting side point is that the man who was behind this LIGO project, his name is Kip Thorne, and was the guy that wrote the movie Interstellar. So in the movie Interstellar, they talk about these gravity waves, this man here. And they say that, in the movie it's all theory. But after the movie came out, like 1.5 years later, purely by accident, we detected this gravitational wave. And everything in the movie and everything this man has worked on in his life and all the equations and all of Einstein's work, suddenly we proved it. It was a massive discovery like 2 years ago. So anyway, that's the explanation of what the gravitational waves are. I don't know if anyone has questions or anything like that.
Interesting. Dimitri, the lens that was at 45 degrees, Is that some kind of glass that lets some of the light through and then bounce straight through and then
Yeah, exactly. So you've got
bounce?
in the middle, you have it's a half silvered mirror, so half the light goes through and half goes
Yeah.
the other way. So the beam of laser light is split. One sec, let me open the
Is
door.
it is it
Someone is coming
is
to
it
research.
split by stripes?
One
Is it
sec.
silvered in stripes or concentric rings or what?
Sorry about that. It's called a semi-silvered mirror, which is, and they're used in communication technology. So semi-silvered mirror laser. This is basically a type of mirror that's coated where it's half the light can come through like this.
Ah, interesting.
And they use these in communications. It's called a beam splitter. And so basically the idea is that the same wave of light is split in half through the mirror. And when it comes back, that same wave of light, interferes with itself exactly. And that's why you get the interference canceled out. And that's called destructive interference. This idea that when you have two waves and they cross into each other, they cancel each other out. When they're the same phase, they multiply, and when they're the opposite phase, they cancel out. So I'll play that the video again of the interferometer. Again, the last part. Let's see here. All right, so and that's how we were able to detect that the Earth was being bent by these gravitational waves. Anyway, I think this shit is really cool that we were able to discover this. And now we've discovered more and more of them, and we've discovered maybe 10 different black hole events over the last 2 years. Anybody else?
No, it's amazing. You wouldn't think that it's possible to get that level of accuracy. Like in the late 1700s, I think there was a thing called the standard meter. I think it's in London that all meters are measured against. But, in the real world, you really can't have two things that are literally the same length.
Yeah, exactly. So this lab was built maybe 20 years ago, and we didn't hear anything. We've been listening for 20 years. We didn't hear any waves. And then basically they had the original version, which was called Initial LIGO, which was less powerful. And then 2 years ago or 3 years ago, they made an upgrade where they made the mirrors way more precise, and they added much more equipment and more stuff to make it much higher level of precision. And once they upgraded this, see, actually the thing is much more complicated than in the simple diagram. It's got other pieces that cancel out. It's got an active dampening system, so the mirrors detect vibration from the outside world, and they actively cancel out that vibration to make it, from earthquakes or, even a small explosion halfway around the globe can trigger it. So we had to cancel that out, these heavy mirrors, and get the precision level high. And once we increased the precision level 2 years ago, then 6 months later we heard the black hole events. So that was the big discovery. They're massive mirrors that weigh 80 kilos. And they're made from sapphire, special sapphire, and they're suspended on these gold wires. It's all rather intricate stuff.
Yeah, incredible.
Well, thanks for listening, guys. Just wanted to have some science.
Thank you, Dimitri.
Yeah, absolutely.
I'm a little smarter. See you later.
See ya.